Newton's laws of motion are actually quite intuitive to you. You may not stop to mathematically analyze a situation, but whenever you move around or manipulate objects, you generally know how to apply forces to attain the results you desire. Newton's laws quantitatively describe those forces and the resulting motions. First, a discussion of force is needed. A force is simply a push or pull on an object. It can be through direct contact or through fields, like a gravitational field or magnetic field. The unit of force used in this class is the Newton. The pound is the English unit. Forces are vector quantities in that they possess both magnitudes, or sizes, and directions. Because forces are vector quantities, multiple forces can act on an object so that they all cancel, leaving no net force. Net forces cause objects to accelerate in a way that will be discussed later. In the illustration on the left, two opposing forces are shown acting on a book that is at rest. Both forces are equal, and since they are in opposite directions, they cancel each other and the book doesn't move. The illustration on the right shows opposing forces acting on the book, but this time those forces are not equal in magnitude. Since the force acting to the left is 2 newtons greater than the force acting to the right, the book will begin to accelerate to the left. If you are standing still, gravity pulls you down, but the floor pushes you up with the same size force and in the opposite direction as gravity. Thus, there is no net force acting on you and you don't accelerate. The forces cancel or balance out. If your legs get kicked out from under you, however, there will no longer be an upward force to cancel gravity and you will accelerate downward until you are on the floor again. Now for a discussion of mass and weight. Technically, the mass of an object is a measure of how hard it is to cause it to accelerate. The more mass it has, the harder it is to move around, regardless of gravity or any other force. The units of mass we will use in this class are the gram or kilogram. Mass is an intrinsic property of an object. That is, it is independent of any environmental factors. An astronaut that has 120 kilograms of mass on Earth also has 120 kilograms of mass on the Moon or anywhere else in the universe. Weight is the name given to the force gravity exerts on an object. Like other forces, it has units of newtons. An astronaut having 120 kilograms of mass, standing on the Earth's surface, would weigh 1,200 newtons. Unlike mass, it matters where an object is as far as what its weight will be. That same astronaut standing on the Moon, where the gravitational pull is 1/6 of Earth's gravitational pull, would weigh only 200 newtons. Newton's first law states that an object at rest, or in uniform motion, will remain so unless acted on by a net external force. Here, uniform motion means motion in a straight line with a constant speed. In other words, it means moving with a constant velocity. If we consider a system, like a car, internal forces among different parts of the car cannot cause the whole car to accelerate. It takes an external force, from something that is not a part of the car, to cause the car to accelerate. The external force in the example shown is that of the wall. The beltless driver doesn't experience this stopping force and continues forward, flying out of the car. Suppose a less violent example is considered, like a car coming to a stop at a stoplight. The force that causes a car to come to rest when the brakes are applied does not come from a foot pushing the brake pedal or even the brake pads rubbing the brake disc. These are internal forces. The external force comes from the road pushing on the tires. This may seem nutty and confusing until Newton's third law is discussed a bit later, but this is the correct way to think about this situation. Newton's second law quantifies how much, and in what direction, an object will accelerate when a net force acts on it. The second law basically states that the acceleration an object undergoes is equal to the force acting on it, divided by the object's mass. The acceleration is proportional to the force acting in it, so doubling the force will double its acceleration. Tripling the force will triple the acceleration, etc. The acceleration is inversely proportional to the object's mass. Thus, for a given force, An object with twice the mass will undergo only half the acceleration. An object with 3 times the mass will undergo 1/3 of the acceleration, etc. The direction of the acceleration is always in the direction of the net force. Newton's third law is sometimes known in popular media as the action-reaction law. Stated more precisely, it says that if object A applies a force to object B, then object B will apply the same size force back on object A, but in the opposite direction. The circumstances or relative sizes are irrelevant. 2 instances of the third law are shown in the slide. On the bottom, if a man walks toward the pier on a boat, he is pushing on the boat as he walks. He thus pushes the boat away from the pier. The reaction force is the boat pushing back on him, moving him toward the pier. A space shuttle pushes hot expanding gas out the back nozzles. What propels the rocket upward is the gas pushing back on the shuttle. In the car example during the previous discussion about Newton's first law, the car's tire pushes on the road. What makes the car slow down is the reaction force of the road pushing back on the tire. This force acts via friction between the tire and road.